Hi everyone, welcome back. So, if you remember in the last couple of videos, we were looking at the wet bulb versus dry bulb and how we could relate heat transfer to mass transfer. And a little bit more specifically, we were looking at something called evaporative cooling, where the process of water being evaporated it will cause a change in temperature. We're actually going to look at another situation that has evaporative cooling, and that's in the case of a cooling tower. So this is going to be a couple parts for this cooling tower, where in this video I'll set up the problem and we'll begin to write some equations for it, and eventually we'll get to actually coding and solving out the differential equations and actually graphing the different temperatures and mole fractions of the cooling tower. So to start out, we'll just draw a cooling tower here. So this is going to be our cooling tower. And in the top here, this is going to be our hot water. Hot water in. And down here is going to be our water out. And then from the bottom, we will have air going up. And this will be our air in. And here we have air out. And in our cooling tower, we will have some sort of packing. And this packing is represented by A, where A is equal to meters squared per meters cubed. And so this A means that for every square meter of it means for every cubic meter of packing, it gives us some additional area where the water and the air will see each other, or will be able to interact, and the water will be able to evaporate. So it allows more contact between the water and the air. So again, this is meters squared of contact between water and air for every cubic meter of packing. And this is throughout the whole column, but I'm just going to draw it right here. Now, actually what we're going to do is, well, I'll label this here. So this is going to be temperature of water in, temperature of water out, and for air, I'm going to label this as G for gas. And this is going to be equal to the actual air that's part of the air. But also in the air that's going in, there is some water vapor that is inside of the air. And we'll just consider this air to be from the environment. So the amount of water that's in the air will be the relative humidity. So this is going to be the gas flow rate of water as well. So these two together make the entire G. So actually, we'll do this just to make it a little bit easier to understand. This will be G in and G out. So gas in, gas out. And again, this is air and the water vapor that is in the air. So this will be TG out and TG in. Okay. So since this air has water in it, since the gas that's coming in contains water, there we have some mole fraction of water, which will be represented by Y. So this is going to be the mole fraction of water in the air. And now that we have this set up, the actual values that we're looking for is we want to know what the change in mole fraction is of water, mole fraction of water, the change in the temperature of the water, and the change in the temperature of G. And we will define this direction here as positive z. So this is z equals 0 up here, and this will be z down here. So this is going to be changes in mole fraction and temperatures per change in z. Okay, so it seems like a lot at first, but what we're going to do in this video is we're going to focus on this dy over dz. We're just going to consider the change in the mole fraction of water. And we're going to break it down into a set of simple steps. And the way we'll do that is we'll take a section here of our cooling tower. So this will be dz here, and this has a cross-sectional area equal to A. Okay, so we know that's what's going into this volume here is G. So we have G going in, that amount of gas. And what we want to get is how many moles of water are going in. So we have G, which is, this is in kilograms per second. So we have this G. We're going to go ahead and divide by the molecular weight, which will give us moles of G, moles of air plus water. And then we multiply by Y, the mole fraction of water. So this is moles of everything multiplied by the mole fraction of water gives us moles of water. So what we'll do is we'll say the change in the mole fractions of water is equal to what? Well, that's going to be equal to the amount, when we have our gas phase that goes in, there's going to be some change in how much water is in that gas phase by the time it comes out. And that change will be from evaporation, from this hot water coming down. And the change in evaporation is a mass transport. So we'll have our mass transport coefficient multiplied by driving force, which is difference in concentration. So this concentration at the surface is going to be the concentration, well, it's going to be the concentration just above the surface. And this concentration infinity is going to be our concentration far away from the surface. So we have this here, and this transport, well, this mass transport of water, we're going to relate that to, well, let's see, I need a second to think about. We need to incorporate the area into here. And this lowercase a. So this lowercase a is from the packing, and this is meters squared of interaction between air and water, or the gas and the water, per meters cubed of this area here. So what we'll need to do is multiply here by this A, which is, oops, there we go. So this A relates this A is from the packing, and this relates the volume of this box here to the area where the interactions between the air and water and the evaporation actually takes place. So since this is going to be meters squared per meters cubed, what we need to do now is multiply by the area of our, or we need to multiply by the volume. And our volume is going to be the area multiplied by the height, which is going to be dz. Now, something that's actually going to make this problem easier is if we define this gas flow rate, instead of kilograms per second, we define it as kilograms per second per meter squared of the column of the cooling tower. And if we define it in that way, then this would give us moles of water vapor per square meter of the cooling tower. Then we would multiply here by the meter squared of the cooling tower, which would give us here just moles of the cooling tower. So we change how we define G, and because of that, we need to add in this A here, this area, in order to keep this the same as it was before. But what this allows us to do is now we can cancel these A's here. So it's actually a bit nicer. And since we define Z as going down, we're going to need to add in a negative here. And that negative is just due to how we define Z. Z equals 0 is at the top, and Z gets more positive as we go down. So this is going to have to be negative. Now, in a small assumption we want to make here is going to be within this, is with this G over M here. We're going to assume that as we move down the column, this gas flow rate divided by the molecular weight is going to be constant. And we did that just to make taking the derivative a little bit easier. We don't have to worry about the product rule or anything. So we're just going to make this assumption here. So these A's cancel. We can take G over M out. We have dy. We have negative A. Now this Kc, or this expression here, the concentration of water vapor at the surface, or just above the surface, we can express that in terms of the partial pressure. So what we can say is the partial pressure, well, it's going to be the saturation pressure of, well, okay, I don't want to skip any steps here. This is going to be the partial pressure of water at the surface divided by RT minus the partial pressure of water far away from the surface divided by RT. And we have dz. So this right here, this is this partial pressure of water at the surface is actually equal to the saturation pressure of water at the temperature of the surface, which we would use something like the Antoine equation to find of water at the temperature of the surface. And again, this is just above the surface. Saying surface is a little bit misleading, but it's the pressure, it's the saturation pressure of the water at the temperature just above the surface. Okay, and we're actually going to call this NW, or the, well, this is going to be the molar flux of water. This is going to be the water, the moles of water that move from this hot water in stream over into the vapor phase in the gas stream that's going out. So I'm going to go ahead and divide by G over M and divide by dz, and what we get is dy over dz equals m negative m times a over g multiplied by nw. And that is our equation for dy over dz. So this is going to be our expression for the change in the mole fraction of water as we move along the column. Okay, so that will be it for this video. In the next video, we're going to look at these two here, and we'll come up with expressions for the change in the temperature of the water and the temperature of the gas as we move along the column. So I'll see everyone in the next video, and thank you for watching.